All right, line P1, we're in learning task 15/16. Learning task 15 is just a picture on one page, and then they kick right into learning task 16. I don't know, it's like a printing error or something like that. We're not going to stress about it. We're just going to treat them all together as a single learning task. Let's start with what is shown on learning task 15, which talks about illustrate instrument transformer connections and calculate the meter readings. The first thing that you need to know as an electrician is that it's very rare that you are going to be hooking up the instrument transformers if it is for Hydro. Hydro has got a completely separate branch that is going to go and be the meter technicians. They're the ones who come in and they are going to place all of these components inside of any sort of a installation. What we might do is we will just go and prep up for that. We will go as far as having to go and mount our current transformers, the CTs, but we will not go and mount or do the final connections. If we do have voltage, high voltage, we will also have to mount the PTs. This is all going to happen inside of a metering cabinet, but all we're going to be doing is to their desired footprint sent by their designer, we're going to go and mount these things in, but we don't do any wiring connections. They take care of doing that all, because if we would go and do that improperly, we could end up with a meter that is going to be either blown up or running backwards. You could actually run the old analog meters backwards. I think that the new digital ones have now got unidirectional current sensing, so that's not a big issue anymore, but it was an issue previously. So what we need to do out of this learning task is we just need to be able to go and understand what the actual connections themselves are going to be. Let's start by examining our main line. We've got a 12 kV line over here, and so we are going to go and take some readings from that. Now, 12,000 volts is ridiculously high to go and have to run any sort of a metering system on. So we don't want to have a voltmeter or ammeter rated for that. We're going to go and use these CTs. If I take a look, this yellow path over here is going to be my primary current path. Everything else is just simply seen as a load. It's just going to be, a meter that we are going to have off of there, but it's going to be seen as just being a very small load to that system itself. So we're going to designate our primary current path. The next thing that we are going to do is we're going to designate each of our metering paths. My voltmeter is simply connecting across from line to line on my main 12 kV. So we're going to drop from 12 kV down to 120 volts. They could place a capacitive voltage divisor inside here if they want it. We could have a cap divider, dropping this thing down, and then that we are going to go and split across that, but in some cases it's not going to be necessary. And then my CT is also going to go and have a primary that is going to be connected in over there, just through the fact that we are bolting on that CT. Let's take a look at our secondary side. Before we take a look at our secondary side, I'm going to start by just erasing a bunch of components, and we're just going to look at single bits at a time. We'll start with our PT. What I have erased here so far is just going to be a bunch of other components that are going to be useful, but let's start by just looking at this thing a single byte at a time. The first little circuit that we see over here is just going to be my 120 volt secondary that I'm going to go and get off of my PT. That 120 volt secondary is going to be placed over top of a meter that is rated from 0 to 150 volts. And so I'm going to go and read 120 volts on there anytime that I would have 12 kV on there. You'll also note that the secondary of this PT is going to be grounded. We're able to ground any single installation at least once. Usually in only one line. Sometimes there have been multiple points allowed in the past, but that's changing. We'll cover all of that in grounding and bonding, but we are grounding down for safety on that other side, so we don't have a floating value of voltage, and this just helps any overcurrent protection operate if we would have it inside of that circuit. We don't here, so we're not going to try and explain that, but it's just a good practice that if I've got low voltage transformers, I'm going to ground down one side. If we take a look at the next voltmeter that is inside of here, the next voltmeter, and we'll just erase everything downstream here and ignore this one, the next voltmeter that's inside of there is going to be rated for 12,000 volts. It is not actually rated for 12,000 volts. What it is just that the paper that's in the back side of that meter, how we have these little hash marks on the paper over there, the meter movement itself is going to be 120 volts. But all that they've done is they have replaced the paper in the back, and instead of having a scale that goes from 0 to 120, they now have a scale that goes from 0 to 12,000 that we are going to have. Still the exact same 120 volt meter though. Just so people don't have to go and make those, calculations inside their head. It's not that hard off of a 120, but to 12,000. But if it was going up to 25 kV, it would get a bit more difficult. So we just place a second, basically, screen up there for them to go and see. The last connection that we are seeing over here is going to be going over to my watt meter. And my watt meter, we're just going to erase all of these so we can see that connection clearly in and of itself. My watt meter itself is going to have a voltage section. Now, I must caution you that up until now, inside of your drawings, what they have done is they've had for a watt meter, they have done this connection that is going across. In other words, they would go and have a metering section, the amp section that would make a connection from here to here, and they would have a volt section that would make a connection from here to here. You will see that standardized setup throughout most of your learning tasks in second, third, fourth. But in this case, what they have done is they have changed where that meter actually is. My voltmeter is across here. My ammeter is across here. You need to be able to read that from the drawing. You should go and draw those little metering sections in, and then that is going to go and help you to interpret the rest of the diagram. If I take a look at this now, you can see that from my 120 volts, I'm going through my metering section and back up. It's really no different than any of those other meters that we saw inside of the section there. We're just connecting to the voltage section of our watt meter. And a watt meter needs to read both voltage and current. If I take a look at my ammeter has a complete current path. I've grounded it down once again, and we will cover that later on, but I take a look, I've got complete current that is going to go and flow through each one of these ammeters. It's a series circuit because we're looking at amperage. Every single one of these has to be connected in series. What I'm going to have out of it as well is, once again, dual meters. One that's going to go and tell me what my actual current is coming from the CT. The other one that is going to have a different piece of paper, scaling it across to 200 amps, because it would otherwise take a little bit of math to, kind of see where our system is instantaneously at. The last ammeter section inside of here that completes that circuit is just going to go and, through the internal electronics inside that watt meter, make that multiplication to become wattage. It looks confusing, the first time that you go through, but if you take a look at each individual meter itself, it's really not so bad. What we are going to have inside of here as well is we are going to have a ratio or a multiplier that we are going to go and create for this whole circuit. And that multiplier is going to be based upon what these are going to be. Over here I've got a 12 kV to 120, and over here I've got a 200 to 5. If I were to go and pull those up on my calculator, we're just going to do that. 12,000 divided by 120 is a 100 to 1 voltage ratio that I have over here. So this is 100 to 1 that we have. We always write for a PT with a secondary of 120. So this would be the way that we would buy them. 12 kV to $1.20 talks about the actual voltage ratings, but the actual internal ratio itself is 100 to 1. Same with this one over here. If I were to go and take my 200 to 5, you could just do 200 to 5 in your head. That will give you a 40 to 1 ratio. What we will be able to do then is we will be able to go and take that ratio that we have on here, and because my watt meter is combining both of them, my watt meter is going to go and have a watt meter multiplier that is going to come off of that. That watt meter multiplier is going to be this times this. In other words, if I were to take 40 times 100, it's not that hard, we can do it mentally as well, but let's just do it in the calculator. So 100 times 40 gets me to a 4,000. In other words, my watt meter multiplier is going to be a 4,000 to 1 that I'm going to go and see out of here. Which means that if I were to go and take that watt meter reading, whatever I'm seeing on that watt meter, if I'm seeing 7.2 watts that's being read by that watt meter, I'm going to take that 7.2 value and I'm going to go and multiply it by 4,000. Let's just try that. 7.2 times 4,000 equals 28.8 kilowatts that my load must be drawing. Same with these ones over here. If it's a 40 to 1 ratio, I'm able to go and read what that would be based upon what I've got coming through here. If I take a look at this 0 to 5 amp over here, let's say it's coming in at 3.5 amps right now. We'll ignore this one. Okay, we'll pretend like we can't read that. Otherwise, we would just read it directly off of it. But they want you to learn about these multipliers. If this was coming in at 3.5 amps, I would take that 3.5 amps, multiply it by 40, and that would tell me that the actual true current that would be traveling through that circuit would be 140. I should be able to read that off of this one directly, but it's a way for you to go and verify. We'll go on to the very last one over here, which is going to be my voltmeter. My voltmeter itself is going to have a multiplier of 100 to 1. If I see on this that I'm coming in at a value of, let's say, 112 volts, that would then tell me that I could take 112 multiplied by 100, which would get me out to a value of 11.2 kV over here. So, yeah, we end up to, that these multipliers allow us to go and carry these things out. Now, inside of an industrial application, what you will often see is that hydro, anytime that there is going to be a place where there is PTs or CTs, they're going to go and take, and historically in the Fraser Valley, it's been green stickers. I don't know why. They've just had green stickers on there. But you'll see this green sticker that is going to go and be placed on the side of the meter, sometimes on the front of the meter, and maybe they've changed that now, but it used to be that, and it's just going to go and have a X80 or something like that that's going to be written on it. I use the example of X80 because it's a common one in industry, but what that is that's the watt meter multiplier. So whoever the meter reading technician is that's coming in there knows that they're supposed to be multiplying that by 80. Now, peeling the sticker off is not going to fool them. They know what's going on. If that sticker's missing, they'll look it up, or if it looks like it's been tampered with. But for you as an electrician, if you see anytime an X something on the side of a meter, you can take whatever your reading is and you can multiply it by that, and that should give your meter reading. In this case, over here, what we should see on this one, make that thing like a green sticker again, is an X4000. Or in a lot of cases, they're going to scientific notation that thing, and they're going to say an X4K off of it. All right. Let's talk about other uses for instrument transformers. Other places that we see instrument transformers utilized is oftentimes when I've got large motors that are going to go and, draw current. Now, you have not been introduced very much in depth yet to motor controls, but motor controls involve the use of current sensing devices. In third year in particular, we're going to go through motors. You're going to find out that as my load goes up on the motor, my amps are going to go up on the motor. And if my amps go up on the motor, that could go and lead to burnout on the motor itself, because we're going to go and have I squared R. We're going to have heat. So we're going to go and want to monitor the amount of amps going in. Now, we don't want to place fancy metering circuits inside this. So what we've done is we've created these things called overloads. Well, we haven't created them. We've used them. Smart people other than us have built them. But these overloads are simply going to go and be little heaters that are placed inside of each line going to the motor. Okay? And so these little heaters are going to pass current through. They're not going to generate a ton of heat because we don't want to be dropping a lot of watts off of our system. But they're going to generate a tiny little bit of heat that is going to go and get applied to either a solder pot or a bimetallic strip. We'll use the example of a bimetallic strip. Bimetallic strip is two dissimilar pieces of metal that are going to be bonded together and are going to expand at different rates. And all that little bimetallic strip is going to do, we'll anchor it down over here, and we'll anchor it down over here, is as it heats up, it is going to go and get more bent. It's going to push further and further up. Not quite to that extent, but you get the idea. What we do with that is we connect that in line with a normally closed set of contacts. So over here, I'm going to go and have an isolated set of contacts that is going to go and be right above that bimetallic strip. And I take the leads for those out of here. When I take those leads out, I'm going to run them to my motor control circuit. So wherever that motor control circuit is, this thing is going to get run through. And these are going to have specialized terminal designations. We'll cover that later on in depth in motor controls. But as I heat up, this strip is going to bend, and what can happen is it can bend far enough up that it is going to go and pop that connection loose, which would be, telling me that I've had too much current traveling through here, because too much current has resulted in I squared R, too much heat. And too much heat has opened that circuit and has shut that motor down for safety. Now, this works inside of smaller motors. They show that, over here we've got a motor that is rated for 40 amps. The size of the overload heaters we would need to have in there for a 40 amp motor aren't that big. But if I go into a massive, massive motor, in this case they're giving me a motor that has got 200 amps, I would not want to have 200 amp direct connection overload heaters. That's what these symbols are. Don't call these the overload. I know that, people refer to that. You're smarter than them. Let's refer to them by the smart thing, which in the circuit, this section is called the overload heaters. So the overload heaters inside of here, they're fine for 40, but 200 amp overload heaters would be ridiculous. First of all, they're going to be incredibly hot. And secondly, they're going to be incredibly bulky and expensive. So what we'll do is we will use a CT that will then take our 200 amps down to a 5 amp. So let's use a 200 to 5. That means that inside of the secondary circuit that we see, this over here, we've got no more than 5 amps that's going to be getting driven through there. If I get up to 200 amps. If I would be, running at less than 200 amps, I'm going to have less than 5 amps. If I go over top of 200 amps, I'm going to go over top of 5 amps. So all I would need to do is have an overload heater inside of here. If I'm monitoring a 200 amp motor over here, all I would need to do is have a CT set up that's a 200 to 5, and then I can go and place a 5 amp heater. That's going to be a tiny little heater, and it's going to be really small, compact, and easy for me to go and monitor. So that's what we're doing inside of all of these systems over here. Very common way that we're just going to go and jump it down. It is really no different than if I had a dedicated apprentice that was just standing over here with a clamp-on ammeter. Okay, that's you with a clamp-on ammeter just watching this the whole time. You wouldn't get distracted. You'd be able to go and watch that clamp-on ammeter the whole day, right? And that you would have your hand on a push button that you could go and shut it off. That's all that the overloads are doing, is they're monitoring the current, and if the current gets out of control, whack, we just take that system right out. They give you an example that's in there with a current of 190 amps, and that they've got a CT that is a rating of 250 to 5. If that CT is rated 255 to 5, that means that it's got an actual value, 250 divided by 5, of 50 to 1. So if I've got 190 amps that is flowing through there, my motor is running at 190 amps right now, it's a little bit lightly loaded. How many amps am I going to go and see out on this side? Well, we just take that 190 and we multiply it by 50. You could also just take it and do 190 by 250 over 5, because that's the exact same thing. But when you do that, it's going to go and tell you that, or sorry, not multiply, divide by, I'm saying this thing backwards, but you get what's going on. We're going to go and divide it down to 1/50th because we're running through the CT over here, which would bring me out to a value of 3.8 amps off of it. Let's talk about another really cool use of instrument transformers. We know all about ground fault circuit interrupters, GFCIs. These are different than the AFCIs, the arc fault ones. Arc fault ones are looking at current that they are going to be trying to monitor. We are looking at the amount of ground fault current or escaped current that is not coming back. We know that ultimately KCL should be met, Kirchhoff's law of current, which states that the sum of all currents that are going to go and enter a circuit should go and leave that exact same circuit. So if I have got current coming in here, this is my AC side over here, and then that current is traveling through all 12, let's say it's 12 amps, should come back out over here. If, however, I end up with a ground fault, and this is where the book goes all wrong. This over here would not be a ground fault. This would be a line fault, because it's ahead of the load over here, which would actually trip out the breaker. So let's just ignore that jankery. I'll white it out carefully on mine. Whatever. I'll just draw thick lines here. We're going to ignore that. If I were to go and have a fault on this side, it would just result in too much current that would travel through. A fault in the ground over here would result in ground current that's going to go back to my transformer and trip it out. We will look at that inside of grounding and bonding. For now, ignore it. Let's talk about an actual ground fault that's going to go and happen on the ground side. And this is where there's danger, because what happens inside of a ground fault is that all of my current that was traveling through gets up to this point, and anytime that there's a junction, my current is going to split. The bulk of my current is still going to travel back through here, but a little tiny bit of it because there is an alternate path, is going to go and sneak its way back out and around. And what I see happening at that point is that I've got a difference in current. This might be 12 amps going through here. This might be 11.9 amps. Almost all the same amps, but not quite what we are looking for. As a result of that, we're going to go and operate. Now, how does it operate? All it's looking for is a net magnetic flux, which means that if I take a look at it, the amount of flux that I'm going to have from current passing through here is going to be canceled out by the current that's going to pass through there if all is good, right? If I don't have a ground fault, I have 12 amps and 12 amps, and I see it's only one turn, one line through there, so my ampere turns, or my phi, my magnetic flux, would be equal. Amperes times turns. A single line through counts as a single turn. So, equal amounts of magnetic flux, therefore they're going to go and cancel each other out, which would mean that according to Faraday's law over here, Eg is equal to BLV, I have got a net of 0, which means that the generated value of voltage should be 0. What we have over here is we've got a toroidal type of transformer. This is a window type of transformer. We don't see that window over here, but those lines are traveling through, going out to that load, and then coming back from that load and traveling like that. So that toroidal transformer right now with 0 flux is going to go and have 0 volts that it's going to go and pick up. As soon as we get that ground fault happening on the correct line over here, we are going to divert some of that current. It is going to go around there. It is going to go around, like what we're showing over here, back to my neutral, which is going to be grounded down. And when it does that, we have unequal amounts of flux, which means that we do have a certain amount of net flux. There's more flux going through in this direction than what I have got going through in the opposite direction, because someone's bypassing. Which means that if there is flux, and if I've got enough turns, there'll be loads of turns on these, then I am going to go and generate a small value of voltage, and that's going to go and kick my circuit breaker. All it's doing is it's sensing off of this. There's going to be a little tiny voltmeter inside of this circuit breaker over here that is going to read that, and then it is going to activate, kick out that circuit breaker. This is why we've got that connection to neutral that we need to go and have on GFCIs. Why we've got to go and have all of our lines going through. If this was a GFCI breaker, to take this down to that point of being a GFCI breaker, what happens is inside of our panel, let's say that this is the connection side. We know that this one's going to go to my line. I'm drawing that poorly there. This connection over here is going to go to my line. This connection over here is going to go to my neutral inside of the panel. This could be that pigtail that we're taking a look at. This side over here is going to go and be my brass screw, my hot screw. This one over here is going to go and be my nickel screw, my silver one, or my neutral. And that's why when we connect up a GFCI breaker, or anything that's downstream of a GFCI, that we need to go and have... Get out of there, Eli. Come on, move. Sorry, Eli's just mangling. That's why when we make these connections, we have to go and connect our neutrals from our circuit to the actual device. So it goes through the device. All the rest of this is just buried inside of that circuit breaker. We don't need to worry about that. And yeah, that second bullet point that they have underneath that, do not go and, say that point X, we will deal with that one later on when we go through grounding bonding. Just remind me about it if I don't remember to put it into a video, and we'll talk about the difference between a ground fault versus a line fault. This was a ground fault on the grounded side of the line. The grounded line is always our neutral. Last one that we're going to talk about is power measurement, or watts reading, anytime that I have got a 3-wire circuit. In other words, a 12240 or an Edison style of circuit. Let's take a look at this one over here. What we see is we've got a single window or a single donut that has been made over here. So we'll just draw that thing out. What we are going to do is we need to make sure that our currents, if I had an Edison type of circuit and I passed both lines through in the same direction, coming from a transformer, this causes issues. We'll talk more about transformers later on, but you have talked about supplies in first year. And if I were to take a look at an Edison type of circuit, like this, you know that AC, we can freeze time, we can have a positive, therefore this point would have to be slightly more negative, and therefore looking down all the way here, from here to here, this would have to be a negative, and in relation to this side, this slight point over here would have to be a little bit more positive. relatively speaking. We got this plus negative, that's going to be our neutral point inside of here. It's positive in relation to this. It is negative in relationship to that one over there, which means that my current is going to go and travel through a load from negative to positive. So the current is going to be, if we froze time, traveling out of here. Some of that current is going to come up there, and then it is going to want to go back in over there. Some of that current is going to go in here. It's going to go up there, up there. It's going to go back this way. I could also have some current that is going to go up here, right? That's going to go and feed in from either the neutral or from wherever the larger of these two currents, whichever one is desired and is going to be larger, is going to go and win for that neutral. But if I were to go and stick a window around the entire thing here, like that, and measure, what I would get would be a net of 0 flux, because all the current that's going out is the same current that's coming back in. What I need to do is I need to twist one of my lines around so that I'm able to go and carry the current back through. Let's do the same thing on this. We're going to go and freeze time for a second. We're going to make this top part the positive. If this section is positive, this one would have to be negative. And in relationship to this negative, this section would have to be a slight bit positive. In relationship to this positive, this section here would have to be a slight bit negative. So we got that neutral defined over there. We can define our directions of current now. We're going to start by just actually removing this wattmeter, because right now it causes more issues than it answers. We will get to its issues when we need them. So we'll just kind of ignore it like that for now. And we'll just look at the windows themselves. As is, like right now without the wattmeter shown inside there, we know that current is going to leave on this line. Current would be traveling through over here, and then it is going to go and enter in here. Some of it's going to enter in here. Some of it could come up and go through the neutral. We don't know which direction it's going to go through the neutral though, so we're going to skip looking at the neutral. We are going to go up here. We are then going to come back on here. Same with any currents that are entering inside here are going to go up through here. Whether the current on the neutral is going in one direction or going in the other direction, we don't know. So we're not going to monitor it. We know that ultimately all the current that goes into the circuit is going to have to come back out of the circuit. As long as we capture everything that's going into the circuit, we're going to be good. So let's just deal with capturing everything that's coming into that circuit. We take a look at our current over here. So we've gotten through our analysis so far. We see that that current goes through and it enters in the same direction, travels through and back to its transformer. So we see that all of the current, whether it's going to be current that's going to be traveling on what we refer to as line 1 over here, or current that's going to be traveling on line 2, is going to pass through that window in the same direction, which means that we are going to get the flux from line 1, phi 1, plus the flux from our phi number 2 over here. Both of those magnetic fluxes get added into this thing together. And as we do that, we are then able to go and see the total net amount that we are going to have. All right, let's now take a look at that wattmeter. The wattmeter is simply, oh man, I have to go and erase a whole pile of stuff here. We'll just clear that all up. The wattmeter is simply going to go and be reading the amount of generated current from here, right? This is a transformer winding that's drawn inside there. We are going to go and read the currents through its amperage section over here. That's going to look like that. And at the same time, we are going to go and be measuring our value of voltage through a voltage section. You will notice that the wattmeter is only able to read a single line at a time, which should be good in 99% of the cases. However, they do have some that are going to be 240 volt rated wattmeters that they're going to have as well. All right. Yeah, that covers us for the power measurements inside of here. How do these things look in real life? In real life, that CT that you're going to see is going to have 2 bars that are going to be inside of it. They're not actually going to reverse the direction of current. They're actually going to go and figure 8 the coil. If you imagine me taking this coil over here, and I don't know if you've ever played Mario Kart 8, you got that big, figure 8 twisted sort of track idea. We would just be twisting our coil. So it would look like, ooh, did I do that right? No, I think I got to go around. I always have trouble with Mobius curves. Yeah, I think maybe that's correct. I can't remember. There we are. I have difficulties drawing some of these things, but all that they've done is they've taken this coil over here and they've twisted it around so that it's going to be inside of opposite directions, and then they pass the bars through. So this bar is going through like that. This bar is going through like that as well. And what that gives us is it gives us a CT, our standard single phase CT, that looks like this, where it's going to be a big, heavy component we place inside of a cabinet, and it's going to go and have bar here and a bar here, and a bar here. And we will bolt on our incoming lines onto one side, and we take our outgoing lines out the other side, to wherever our loads are, sub-distribution, etc. But all that they've done is they've taken this thing and they've twisted it around, because it would be way harder for them to go and twist the actual bar around, and it would be super confusing for us as electricians. I'm not going to lie, it would be. We would screw it up if we had to feed. Otherwise, we would need to feed one line in from here and then back out to the other side. You're asking for problems at that point. Last thing that I want to go back through all of these drawings real quick on is just to go and note what we have here for transformer polarity. Transformer polarity dots are always going to be associated to the same line side, and they're going to be associated with a transformer dot on my wattmeter section. Over here, I see that I've got my wattmeter section that is lined up. Over here on this voltmeter over here, I'm going to go and have that attached to the same line that I have these dots on. See how that one there is the same connection down to those dots over there? We'll see the same through, not so much that one and not so much that one. This one does have transformer dots on it technically, but it wouldn't be as necessary as AC. Really, it's going to become a bigger issue anytime that we're dealing with the AC. Let me just erase a bunch of the extra stuff we don't need to see on here right now. And let's just go and verify that all of our dots are on the same line. This is my line that I'm choosing to go and identify. I'm just going to put an I over here for identify. I see that my PT has got its dot attached to the identified. I see that my CT has got its dot attached to the identified. And then on the other side of my PT, I see that it's got its dot attached to the identified section of the wattmeter. And on my CT, it's got its dot attached to the identified section of the ammeter over here. That's it. That covers us off for these components over here.